allow you to set the values of the variables, and they will also allow you to check the values of the variables sometime during the execution. So that is somewhat analogous to this idea in hardware. Now, I was mentioning that you could use a D algorithm for sequential circuits, and you will find that in the literature. Now let us consider an interesting problem, the question of initialization. Now when you turn the power on, what can you say about the state of a flip-flop? Is it going to be 0 or 1? Which turn the power on. But what do you think? An answer is we don't know. Well, we turn the power on depending on how charge distributes. So a flip-flop would wake up as 0 or 1, we don't know. It could be technology dependent. In practically all cases, there is some initialization implemented. And now there is, so you have a finite state machine. How do you get your finite state machine into a known state from an unknown state that you will have when you turn the power on? And answer is that the usual approach is that you have a reset mechanism. In practically all devices, so if you have a PC, you have a reset thing. And of course, when you turn the power on, it includes a reset. And so reset basically will cause initialization of the storage elements. And once the storage elements are initialized, then they will have a specific response. Other possibility is that you could have some, you could apply an input sequence to get the circuit in a known state. So you have a circuit in an unknown state, you apply some set of inputs, and eventually you will be able to get it into a known state. And that is a very interesting theoretical problem, and you will find that discussed in some of the literature. But this is, for all practical purposes, you will always have a reset mechanism. Reset, and your circuit will go to a known state. Now there is a possibility that your reset mechanism may be bad. So if you have a bad reset mechanism, how are you going to test for it? Because the behavior is not predictable. So what can you do if you have a bad reset mechanism? And the thing is that a rigorous analysis, when a reset mechanism is bad, is very hard because we don't know what it will do. However, in practice, it should be very detectable, because if reset doesn't work, whatever your unit is going to behave very strangely. So you should be able to detect it without too much difficulty. So reset mechanism takes care of the problem. Any questions or comments? Okay, now let us talk about functional testing of finite state machines. Now, so far we had assumed that we know the structure, but what if you want to do a functional testing? So basically you are given the state table. That's all you have. Now there are actually two possibilities. One possibility is the states are observable. And other possibility is that the states are not observable. There's a B there. If states are observable, then it becomes a much easier problem, because you can apply different inputs and see if it goes through the states. If states are not observable, then it is more challenging, because you need to somehow do whatever is necessary to make sure that it was in a certain state. And so if you have a state table or a state diagram, so your things could be, I don't know, something like this. I'm just creating some diagram. Now, how do you know you have tested it thoroughly? Let us say if you have n states. So sometimes people will count how many states you have traveled. So if you have gone through a state once, you will say that you have exercised it adequately. But if you think about it, that is actually not that reassuring. You should probably check for all transitions. So you should make sure that this is correct, this is correct, this is correct, this is correct. Make sure that all the transitions are correct, and that means for all input combinations, the outputs are correct, and it goes to the correct next state. This incidentally is a problem that applies to hardware as well as software, because software behavior is often described in terms of a state diagram, and it is also applicable when you are testing a communications protocol, because the communications protocols are also often described using a state diagram. Any questions or comments on this? Okay, now let us talk about testing complex systems. So far we have talked about, okay, you have a few gates, if you flip-flops, but what if you have a complex system and incidentally I should mention, there is a quiz that is available on RAMCT. So it should be available at noon today. And so you have until I believe Saturday afternoon to take it. So go ahead and this quiz may take some work. And also there should be a feedback module, an assignment with several problems that should be coming up soon, perhaps next time. But go ahead and start working on that quiz, and that will get you prepared for the assignment, which will get you prepared for the test. And I guess that is supposed to prepare you for the real world. So I guess that is the ultimate aim of everything that we do. So the quiz on RAMCT. And okay, has the RAMCT been working okay? So I think you have all taken the previous quiz. Incidentally, on RAMCT you must have found out already that I have put some of the slides available. So in RAMCT in discussions you will find slides. I think these are not there, but I will go ahead and put them in there. So let's talk about complex systems. So basically a complex system has a number of components. So with many components. So for example, a computer is an example of a complex system which has a processor, and the processor is a complex component because the processor has a number of different things. So a processor has a number of registers, PLAs, some ROM, some storage elements, and so on, a control unit. Approach could be something like this. Assume a fault model for each component. So basically, decide what faults you want to assume for each of the components, and come up with a system fault model based on component fault models. And basically you consider the interaction of the components to come up with the fault model for the components. And then you need to come up with a testing strategy and in your testing strategy you need to test each component individually. So somehow, one way or the other, you need to test each component sufficiently well, and then you need to test for the interaction of components. And okay, so what is a component? Now there are some, there is quite a bit of literature available, and when we say a component could be a physical component, or it could be a segment of functionality. Or it could be a kind of something that is maybe not physical, but it's a part of functionality. So when people started thinking about testing microprocessors, so when microprocessors came, a microprocessor by definition is a processor which is all included in the single chip. So the people started thinking about the problem of testing complex systems, and people figured out some approach for testing microprocessors. And so this is the sort of approach that they came up with. Okay, so you have a bunch of decoders there, you have the control unit, you have some registers, you have a register array, and they figured out a fault model for each of them, and they figured out a kind of a strategy for analyzing all of them. And that actually brings us to how do you test a complex system. And one possibility is to use an incremental testing approach. And so for example, if you will look at how they had proposed that people should be testing microprocessors, would be this.